Hello everyone. In this video, I'm going to be covering me going through an exam, the 2016, and I'm just going to be just showing you my logic and just explaining things as we go along. So let's just get right into it. So nomenclature should be the easiest section for everybody. Should be 3 points, but I always end up losing points on it, ironically. So the first molecule we have, our priority goes from having aldehydes, then ketones, and then everything after that is normal. Okay, so we have aldehydes, ketones, alcohols, alkenes, and alkynes. So on this first molecule, we have a ketone, we have alcohol, and we have a this benzene ring here. So if I am numbering it, right? So this is the correct numbering. I forgot to erase this. But our ketone is the highest priority group that we have so far. So I need to number this as close as possible to the earliest point in the chain and the longest chain. So the chain that contains the ketone and is the longest one, and the direction that has the ketone earliest is this direction and this chain. So 1, 2, 3, 4, 5, 6, 7, 8. And then from here, it's pretty straightforward. So we have, okay, so I have a 8 hydroxy group, and I also have a 6. And so whenever you have a benzene ring that is a substituent and it's separated from the parent chain by one carbon group, so one CH2, so like what we have here, we have a CH2, and then we have the benzene ring. This is called a benzyl group. Okay, the other group where it's just a direct attachment of a benzene ring substituent, it's called phenyl with YL, not OL. Okay, so the full name of this molecule is going to be called, if we label this correctly, so I have the 6 hydroxy, so I have 6 benzyl, 8 hydroxy, and then the parent chain, so there's 8, so that's octane, and so I replace the E with 1. Okay, so 8 hydroxy, oc, and then the E, octane 1, right? And I actually forgot something, right? So I have to also indicate the location where it is, so octane 2, 1, okay? All right, easy peasy. And so now we have this one, so it's not drawn completely nicely, but I have a benzene group. I have a ketone group, I have the aldehyde group, and I have a double bond. All right, and I also have, stereochemistry here, so I have to be careful about that as well. So first thing I want to do is I'm going to take care of the stereochemistry. That's how I like to do it. So obviously the first thing that is going to be the best here is going to be this carbon right here, right? So I'm comparing hydrogen against a carbon, against a carbon, against another carbon. So so this one is a carbon connected to 2 oxygens and a hydrogen. This is a carbon connected to 2 hydrogens and a carbon. This is a carbon connected to 2 carbons and a hydrogen. So this is going to be 1. This is going to be 2. Okay. This is going to be 3. This is going to be 4. Right? And our hydrogen is on a dash, so we don't have to worry about that. And so if I go 1, 2, 3, right? This is R. Okay? And now let's do the rest. Okay? So you can faintly see my numbers already. So once I discover, first I need to discover is where the parent chain carbon numbering is. So from doing that, aldehydes are above ketones. So this is the aldehyde substituent. This is going to be number 1. So from here, after you find the parent, you don't have to worry about, oh, ketone is higher than double bond. No, it's just numbering. After you find the parent chain, everything else is on equal standing in terms of numbers. So we're just trying to find the lowest number after this point. So if I go in this direction, I get 1, 2, 3, 4, 5. So I get 1. And if I go in this direction, I get 1, 2, 3. Okay. So this direction is the better one. This direction. So this way, the clockwise way. All right. And then on this, what do we have? Okay. So I have the 1, 2, 3. Probably number it. So this is 1, 2, 3, 4, 5, and 6 is up here. And so this is 5 oxo, right? Anytime you have an aldehyde or a ketone and they're not the parent and they're a substituent on the parent, it's always referred to as oxo, okay? So whether a ketone is on the parent chain or on the substituent chain, it's referred to as oxo if it's not the parent group, okay? And if a aldehyde is on the parent chain and it's not the highest priority group, it's also referred to as oxo. And if it's on a substituent, it's referred to as formal, okay? And so we have a 5-oxo group, right? And then I have number 1, and I also have the R. So we can start naming this now. So 1R, okay? And then I have the double bond is going to be in the parent name, right? And then I have only this one substituent. So I have 6 oxo, and then I have cyclohexane, okay? And actually, this would be the place. So since it's a I spelled cyclohexane. Right, so cyclohex, and then on carbon number 2, we have the double bond. So cyclohex 2-ene, right? Okay. Oops. Sorry, guys, I'm kind of tired. All right, cyclohex 2-ene, and then since we're trying to include the aldehyde as the parent on this ring, we always give it the name carbaldehyde. Okay, so on any chain, any ring where we have an aldehyde coming off of it, and I want to make refer to that ring, make it a parent, right? Include the aldehyde in that ring as the parent, refer to it as a carbaldehyde. So this structure right here is a carbaldehyde, and obviously we have to do this because there's no way that we can, include an aldehyde within the chain itself. It's always going to be coming off of a ring, right? A ring cannot have an aldehyde directly within it. It's going to be a substituent off of it. But we still want to include that priority of that ring being what it is, right? I mean, aldehyde being what it is, the highest group on here. So we refer to these as carbaldehydes. So, cyclopentyl carbaldehyde, cycloheptyl carbaldehyde, so on and so forth. So just the cyclohex whatever, and you include the components within the name that you have to. So the double bond or triple bond, and then you add the carbaldehyde even after, and you include the E, right? So just directly afterwards. Okay. Now the next one is you need to know your derivatives. So we have 2-nitro 6-phenyl anisole, and anisole is a benzene ring with an OCH3 group on it. Okay, so on this is number 1, okay, and number 2, they say 2-nitro. So nitro is the NO2 group, and then 6-phenyl, so this is going to be right here, and phenyl is just another benzene ring, so the direct attachment of another benzene ring, and this is what we would have, right? Easy peasy. Okay, Label the molecules below as aromatic, anti-aromatic, or non-aromatic. Okay, so first one that we have is we have this ring right here, okay? So first thing first, we have to check if everything's sp2 or not. And when we do, we find that this is not, this is sp3 right here. Okay? But it doesn't really matter because it's a lone pair. And it's a lone pair with a negative charge here. It's a negatively charged, because of the lone pair. And so whenever you have a charge, right, a negative charge in particular, you have to resonate it. You have to see it's automatically going to be included in the total number of pi electrons in the ring. So this is 2, 4, 6, and then that's it. So we have 2, 4, 6, and so that's 6 pi electrons. All right, and 6 pi electrons fits into the 4n plus 2 rule. If n is 1, I get 4 plus 2, that's 6. So this first one is aromatic. All right, so 6. Second one here, we have a sulfur, I have a nitrogen. All right, and so this nitrogen is already sp2. The sulfur is sp3, however. Okay, if anyone's confused how to determine something sp3 or sp2, so for example, if you have an oxygen, right, and it's a neutral oxygen. This neutral oxygen is sp3. So what you do, all you do is count the number of groups. So I have this bond, that's 1, another bond, that's 2, this group is 3, this is 4. And so S is 1, and then P3. So we have a total of, so it's like S1, P3. So there's a total of 4, and all in all. That's how you calculate these things. So, a double bond, right? Let's say we had this, okay, whatever. This is sp2. So, well, this is actually not sp2. It's less than that. It's just sp, right? So I have 2 groups on this carbon, that's sp. If it was, this would be sp2, right? This is a normal what a double bond is. As double bonds are always sp2. So I have 1 group, 2 groups, 3 groups. So that's sp2. All right, just quick review for those of you who don't. I just want to cover everything. All right, so now this is sp2, right? So now this nitrogen is already sp2. We're not going to consider this lone pair because there's no reason for that to come in, and it can't. This is already fully sp2. There's no room for it to just come in here. Okay, so this is not going to come in, and it doesn't need to. It's already sp2. So we have 2, 4, and if I bring this third one in, it becomes 6. So because this is in the end a total of 6 pi electrons, and we have to bring it in, right? I always want to consider the 2 states. So this first one, this ring, starts off as non-aromatic because we have an sp3 atom in the outer ring. If I bring in this electron, then we can make a decision. We can make it either anti-aromatic or aromatic. And because it ends up being 6, it's aromatic. And because of that, then yes, it stays as aromatic. But if it ended up somehow being 8, right, and it would end up being anti-aromatic, we would not choose this because anti-aromatic is a lower stability than non-aromatic. Because remember, the stability is aromatic, non-aromatic, anti-aromatic. And so this ends up being 6. This is aromatic. All right, now let's look at this one. One thing you need to know is that boron is satisfied with only 3 bonds. So it's always going to be sp2 by itself like this. So this is sp2. So we have a total of 2, 4, 6, 8, and this is a total of 8 pi electrons. Nothing I can do. This is going to be anti-aromatic automatically. All right, last one. So I have 2, 4, 6, and now this is a sp3. So I need to consider bringing in one of these lone pairs, and so this is going to be 2, 4, 6, 8. 8 in total. And so because it starts off as non-aromatic because we have an sp3 atom, right? And then when I bring in the lone pair to make this all sp2, right, to follow the rules to be either aromatic or anti-aromatic, we see that it becomes anti-aromatic because there's a total of 8 at this point, right? And because it becomes anti-aromatic, I prefer not to do this, and so I stay as non-aromatic. And so this is going to be non-aromatic as a result. Moving on. Rank the following substituted benzene compounds or of increasing rate in a reaction with a mixture of Br2 and FeBr3. So this is electrophilic substitution, and we're brominating benzene rings. All right, and so this is dependent on the strength, right? So it's dependent on. I need to erase all this bullshit. All right, so I erased it. Okay, so we need to remember that in electrophilic substitution, right, where the benzene ring is acting as a nucleophile and attacking an electrophile, right, and all these reactions, like an NO2 reaction, the H2SO4 reaction, the FeBr3 reaction, the Friedel-Crafts reaction, we create electrophiles that the benzene ring can become nucleophilic enough, to attack it, right? So the benzene is already has nucleophilic ability, but it only is nucleophilic enough when the electrophile is actually electrophilic enough, right? So better the electrophile present, the easier the benzene ring can attack it. But what can help this is the activated. So important is the presence. Okay, so we need activating groups on this ring. So activating groups are going to increase the electron density by donating electron density into the ring and making the ring more nucleophilic, and therefore it's going to react faster with electrophiles outside. So we need to look for the, either the most donating or the least deactivated ring. Okay, and so first we need to look at all these substituents. So this is a withdrawing group, right? I have a carbonyl structure, right, directly attached to the ring, withdrawing. I have a nitrogen, has a lone pair. Nitrogen always has a lone pair. And so this is also a withdrawing group, carbonyl directly attached to the ring. So direct attachment withdrawing group, direct attachment of withdrawing group, donating group, right? This lone pair can go into the ring. This is what a donating group does. It has, a lone pair that can go in the ring, and it can help the ring act as a nucleophile, right? And it stabilizes the ring once it loses one of these bonds. You need to understand how that works, but this is essentially going to be 3, because the only one out of these 3 that has a actual donating group attached to the ring. Now, choosing between this one and this one, how do we make that decision? Well, we make that decision based on how withdrawing this is. So I have 2 carbonyls. These are exactly the same. I think we can all agree that this carbonyl is exactly the same as this carbonyl. However, this carbonyl is on its own, only attached to the ring. This carbonyl is attached to the ring and also to another nitrogen. The structure is called an amide, but it's not very important right now. Essentially, to cut to the chase, this one is going to be the lowest rate. This is going to be the second. And this is because this is fully withdrawing, right? This ring can always end up being withdrawn into this carbonyl. However, this carbonyl is sometimes in a resonance structure with the nitrogen. So sometimes the nitrogen is forming, just to show you, it's forming, that double bond, and then I get the O minus, right? This is the withdrawing structure. And so that means the benzene ring at this point cannot, give density, go out and be withdrawn into the structure, because this is blocked now and this is already being withdrawn. So let's say 50% of the time is it actually available in this state for the benzene ring to come out and actually be withdrawn, and this actually acts as a withdrawing group on the benzene ring. Other times it's in this structure where it's with the nitrogen, right? And so this is what we have. And so this is why this is 2, because this withdrawing group does not get to act like a withdrawing group all the time. It does not get to act like a withdrawing group all the time. And so unlike this one where it's fully acting like a withdrawing group all the time, this is why this is 1. It's the slowest, and this is 2. Okay? And so that's the explanation for that. It's not directly 50%, but we're just saying in understandable terms, just to give an example. All right, next one. Explain why compound A is more basic than compound B. Your answer must include structures to support your reasoning. All right, so this is what I was worried about. So basically, compound A is a carbonyl right here. Okay, and compound A also has a double bond right here. Right? And yes, I have this O, this lone pairs. All right. So why is compound A more basic than compound B? Okay. Well, let's try to understand. Okay. So what essentially we're dealing with here is the formation of we have this structure in both, right? And what we're looking at is this oxygen donating a lone pair and resonating with the carbonyl. Okay. So we're looking at this essentially. So this happens, and then this comes out. And what we get is this resonance structure where we have O minus, and then we have O plus. Okay? All right? So this is what we have essentially in B. All right? B looks like this. All right? A looks like this. Right? A is the exact same thing. Okay? And so A is like this. All right? Okay, so what this is getting at essentially is honestly a kind of weird question because which oxygen is the one that's being basic here? Is it this one or is it this one? And I'm pretty sure it's this one that we're going to be looking at. So in carbon A, I mean molecule A, right? We have the potential for an aromatic structure. So I have this is this was originally, this is sp2. This is sp2, this is sp2, sp2, sp2. Only thing that's not sp2 is this oxygen. And if I make it sp2, right? If I make it sp2, I can just donate one of these lone pairs in and we'll have a total of 6 pi electrons and we'll have a fully, aromatic structure. So if these go in, okay, and so this displaces this over here, this will go in over here, and then this will come out over here. Right, so ignore one of those lone pairs. Right? Negative charge. Okay, imagine it's a negative charge. And this is going to come out over here. And so we're going to have this now. Right? And then after this is going to come in over here. And this is going to come out over here. Right? So we have this. And really, realistically, right? I have this final one. Realistically, um, we can have this dipole moment created from the beginning, where we have this carbonyl is is separated into this goes up into here. We can have this from the very beginning, and we can just have a carbocation, and this ring is fully resonating that carbocation around, right? We don't really have to deal with the negative charge too much. Um, okay, um, so with this structure, right? the reason why A is more basic than B has to do with the aromatic nature, okay? And it's a little bit of a stretch, but essentially the aromatic structure allows for a more stable resonance structure and therefore allows the dipole moment to be greater as a result because the resonance structure where where this is separated into its charges is contributing more, and so this is more present than in this, right? Um, and that has to do with the aromatic structure of the ring, allowing the charges to be delocalized around the ring. And so because it's aromatic, it allows for that delocalization and allows for that stable structure to be created. So it allows the negative charge that is created on the oxygen to be more present. Whereas in B, it's not as stable. Those charges that are created are not stable. They're only non-aromatic, right? And it's just a normal molecule, and it's just constantly resonating, back and forth, you know, from here to here to here to here to here. It doesn't really stay in one stable form or another. Whereas in this form is our non-basic form, really, right? These are a little bit these atoms are a little bit basic, but when this is contributing in the ring, and this can be up, and we can have that full separation of the charge, right? We have an aromatic structure that is created, and that allows us to have this structure, present fully, right? This has to be in this form in order for this structure to be fully aromatic, because this is, these bonds are conjugated, so they're going to be moving around. And so this aromatic structure lets us have a more basic molecule. And that's the kind of long, complicated explanation for why A is more basic than B. And you could have said this very simply in saying, well, because A is aromatic and B is non-aromatic, then the resonance structures for A, where a dipole moment is created or a separation of charge is created, and we have a negative oxygen, that structure, it contributes more to the overall resonance structure of the whole molecule. Whereas B, the O minus in the O minus resonance structure is not as present. Okay, so complicated answer, but I have a key up, and my key is not as clear because I also I was a little bit stumped by this question myself when I was doing it back in Orgo 2, but that is the general explanation. Okay. I'm gonna be honest, I'm not too comfortable with the whole dipole moment stuff, but it does make sense to agree. It has to do with the resonance contributor, which is what is a better resonance contributor. Anyways, already 30 minutes into the video, gotta move on. Place the following compounds in order of increasing frequency with the C double bond O stretch. So there's ring strain increases frequency, resonance decreases the frequency. So conjugation, right? And so this is ring strain, this is ring strain, no ring strain. So this is going to be the lowest frequency, right? So it's resonance and not on the ring. This is going to be right here the highest frequency because it's ring strain but no resonance. This is ring strain with resonance, so this is 2. Okay? All right, now reactions. Change the pen to a little bit smaller color. All right. All right. So first things first, right? What we have here is just making sure everything's correct. Okay. So we have H2SO4 fuming. This is going to add an SO3H group to the most activated ring. The most activated ring is the ring with this group. It's a donating group. And so what that's going to do is add a SO3H group to our ring. Gotta draw all this over and over. And so we have that OCH3, and so we just add the SO3H. All right. Next step is LiNH3CH3OH. So this is Birch reduction. So we're just going to reduce all these rings. And our priority is to not let the rings be having the double bond touching a withdrawing group. Okay, so gotta erase this. Okay, so we have that OCH3 group, have that SO3 to the right, but so I don't want to touch this, but I also want to try to maximize touching as many donating groups as possible. So this first one, this is the best way to do it, right? You could have also done it, this way. Doesn't matter. It gives the same thing basically. Okay, and then for the second one, we have a BR, and that's all we have. And so the BR is also a withdrawing group, so I don't want to touch that. So I'm going to be doing this. Okay, so I'm oriented like this way, and then this last one has the NO2 group over here. And so I don't want to touch that, so I'm going to orient my double bonds like this. Okay, I hope everyone can kind of see it with how crappy my rings are. But this is the ring, and the double bond is going to be, for anyone who can't see it, this is the way that this bottom one is going to be oriented. Okay, so away from the NO2 group as much as possible. Alright, next one. Step 1, CH3O minus Na 100 degrees Celsius. This is the addition elimination, right? I have withdrawing groups in ortho or para. So I have two leaving groups. I have a chlorine and I have bromine. Which one do I choose? I choose the one that is ortho or para to the most withdrawing groups. So this is the only one that is para to a withdrawing group, so I choose the chlorine. And I leave the bromine alone. Okay, and I add an OCH3 group. Step 2, HNO3, HSO4. This adds an NO2 group, right? So we add another NO2 group, and I find the most activating group. So this is a bromine, this is NO2, this is the most activating. So this is going to direct the positioning. So I put my ring again. So I just do ortho. I only have ortho, it's ortho pair directing. The pair is blocked. This is ortho blocked. And so this is the only position. So I'm going to add NO2 group there. And that's the answer for that one. Okay. Step 1. So we have this. We have Na2Cr2O7 H2SO4 100 degrees Celsius. This is oxidation of side chain. So this is a T-butyl group. It's unaffected. OCH3 group is not a carbon, so that is unaffected. Okay, this becomes that. It becomes a carboxylic acid. It always becomes a carboxylic acid. T-butyl group is left alone. Step 2, SOCl2 turns a carboxylic acid into an acid chloride. So have a carboxylic acid. We just replace the OH group with the Cl group. And then step 3, we have some R group to CuLi. This turns acid chlorides into ketones. So our answer is going to be get all the other crap on there. And then we have the ketone. So you basically just replace the chlorine group with whatever group is in here. And so we have this. All right, and this is our answer. All right, And now moving on. Okay, so we need to be able to know the steps required to do this. So I need to know, right? Here I have a hydrogen. This is a hydrogen here. And then I have this group. And then I have a ketone. So how do I turn this? So this is diethiene, use of diethiene to synthesize ketones and aldehydes. So what do? The first step is always, the first two steps are always the same. First step is BULI, butyl lithium, right? This will, and you need to know what it does because you have to show the steps. So this is going to deprotonate this, take off one of the hydrogens and give us a negative charge. Second step. Second step is the SN2 step. So what are we going to use for step 2? Well, we're going to use the group that is added here. So this is what we're going to have. And so step 2 is going to be so just draw this right here. Right? That's all you're going to have for step 2. And so that's what step 2 is going to be. And because it's an aldehyde, we only repeat this once. And then we directly go to the third step, which is H3O plus HgCl2. Okay? So you may say, what does step 2 look like? Well, it looks like this. Okay? So we attach it right here, right? So I have that addition to that carbon, and then one carbon away, I have both this. All right? Not too bad. Okay? All right, and then this would give us our answer. Easy peasy. So you need to memorize these steps. BULI, some RX, that is always has to be primary, right? At least a primary or methyl. And then HgCl2, H3O plus will give us the ketone or aldehyde, depending on if you do these first two steps once, you get an aldehyde. If you do it twice, you take off the other hydrogen and it becomes a ketone, and we add another R group. All right, 5. So O3CH3 2S, this is Orgo 1 reaction. So both step 1 and 2 are combined. It turns alkenes into carbonyls, right? So oxidation. Okay, so the bond gets oxidized. We get 2 carbonyl groups that are there. Here it ends up being an aldehyde as a result. Right? It does not fully oxidize. Okay, and then the next step, ZnHgHCl2 equilibrium. So we're going to be doing a reduction here. So we need to get rid of our carbonyls, and that is going to give us this. Okay, so that's that step, right? And then we have step 4, Br2 and light, and so this is going to be brominating our benzylic positions. Always this position, right? And then step 5, NaCN. That's a SN2 reaction. So it adds CN group. CN group. Okay, and then CH3MgBr, HCl+. So this converts this into a ketone with the addition of the R group. And so I'm gonna erase this, okay? You have to show this separately, but I'm just gonna erase it because I don't want to write anymore. And so what this is going to do, so this is going to be gone. This is gone. Alright? And then we turn this into a carbonyl. And then we add the R group. So alright, that's our answer. So we have this funky looking thing. Alright? Not too bad. So that's Grignard plus HCl plus converts a CN group into a ketone. Alright? Step 1. Alright? HCl, CO, AlCl3, CuCl. What does this do? Well, I forgot to erase it. Silly. So this is going to add an aldehyde, right? And it's going to add it. So ignore this. This is not supposed to be here. It's supposed to be here. I'm sorry. This is going to add the aldehyde to the ortho position, right? This is not sterically hindered, so it needs to be here. Step 2, CrO3, H2SO4, H2O, acetone, 0 degrees Celsius. This is Jones. Jones is not strong enough to oxidize the side chains, but it is strong enough to turn an aldehyde into a carboxylic acid. And you know that you have a carboxylic acid the next step because this third reaction, if you know your reactions, this is only for carboxylic acids. So the third step is conversion of carboxylic acid into a ketone. So our answer is going to be so we have this, and then this, and then we have phenyl group. Okay, I'm too lazy to write it out. Do not do this on your exam. You're not allowed to do this. Show the whole structure. I'm just doing it because I'm lazy right now. Phenyl is just a benzene ring. Okay, so CH2 and then benzene ring, and that's it. Okay, you need to be careful if she has these as separate steps. So if this was step 3 and then step 4 was H2O plus, you would have to show the 2 steps, and essentially what it looks like is O minus, your R group that is added from the Grignard, your original R group, and then you have O minus, Li plus, Li plus. This is the lithium salts that form. And then HCl plus will protonate both of them, and it will decompose into a ketone. Right? Alright, now mechanism. This is going to be so fun for me to do with my pen and mouse. Alright, so mechanism, we have the conversion of a ring into, basically it attacks itself, right? The molecule attacks itself, and we have HCl here. And so what the first thing that we need to recognize is our understanding that to make a ring attack something, we have to make a good electrophile. And in all the cases, almost, a good electrophile, especially from what we learned about Friedel-Crafts, a good electrophile is usually a carbocation. A carbocation is an excellent electrophile for a benzene ring to attack. So if I have that in mind, I know that a carbocation is what I need. That's my goal, right? I know that I'm going to be forming water. And I know that water is a good enough leaving group whenever it's on a secondary or tertiary carbon, and that it can leave by itself without having to be helped to leave, right? And if it does need help to leave, we will simply have a hydride shift that allows water to leave. If this was on primary, we'd have a hydride shift that concurrently allows the hydride shift to occur and the water to leave, and transferring the carbocation from the primary to a secondary or tertiary, whatever it is. Anyways, so to make this a little bit darker. So one of the lone pairs on the oxygen takes the acidic hydrogen on hydrogen chloride, and then chlorine leaves, and what we form is this. And y'all are gonna have to put up with my handwriting for this. Very important mechanism not to use donut. You should show and make sure you can keep consistent with where they originally had those bonds. It won't change your answer really because in all reality, this is always moving around. So, you'll get the right answer regardless. That's just how it works. This is the first step. All right, but just keep consistent. That's the main point. All right, and now what's the next step? The next step after this, I need to make sure that I know that this is going to attack this. I need to make sure that it forms a six-member ring. So I need to count. This is 1, 2, 3, 4, 5, 6, 7. I make a six-member ring, not a seven-member ring. So I know that I have to move something over. I need to move this one more to the left, make it 6. And so obviously the only thing that's going to do that is if I have a methyl shift. So I'm going to draw a line out of this bond and I'm going to draw it to the carbocation and put methyl shift on the arrow. Right? Wonderful handwriting. Okay. Now it is here. Now it's time to count. Right? And this would be 6. So this makes a six-member ring. All right? And so all that happens is that this double bond is going to come and it's going to attack. Right? So the next step, all right, is the formation of that ring. This is where it gets fun. Because now we have our resonance structure, our beautiful resonance structure. And so I'm just going to draw another ring attached to this. Okay? And so off of carbon, we said this is 1, right? This is 2, this is 3, this is 4, this is 5. And now we have addition of connecting this to 6. So this is 5, 6. So off of 5, I have a methyl group, right? And off of also 5, I have this group. 5 had the carbocation. I broke this bond to attack. So this no longer has a carbocation. And now the carbocation moves to where? Carbon 1. Right? Carbon 1. Carbon 6 never lost a bond. This bond broke and it formed it. Right? Carbon 6 to carbon 5. Carbon 1 was double bond and had this. So the carbon 1 is the one that lost the pair of electrons. Okay? So carbon 1 is deficient now. And very important at this point to draw out the hydrogens. So carbon 1 on the benzene ring here. Well, this is 1 right here. This carbon never had a hydrogen on it because it had the R group. This carbon also never has a hydrogen because it has the methoxy group. And this has a hydrogen. Hydrogen. There's invisible hydrogens here. So we know there's a hydrogen right here. All right? Very important for later on. But first things first, we're going to show resin structures. The first resonance structure is this one. So we're doing this, that. Okay. And get a plus charge. And then at this point, we can go 2 paths, right? So we can you can either do this as one concerted, line of whatever, or you can branch off, I think. So right here is the very important one. And I think it says and be sure to draw the most stable contributor, right? Right? And so what you need to write, so this is going to come in here, and so what this is going to form, right? And make sure you're always showing your charges. going to form that. I'm just going to stop drawing it like this. All right. Okay. And so now I'm going to write major resonance form on top of this one, just so they know that this is the major resonance form. This is the only form out of all these that has an octet, right? It's this one. And then from here, this goes back up, and I get this again. And so really what you have is here, we have path A, path B. This is A, this is arrow A, this is arrow B. Okay? And so from this one, you can show 2 directions. This is perfectly fine. I did this on my exam, and I got full credit. This is acceptable. Perfectly acceptable. I don't need to redraw structures that, serve no purpose. So form this, and then we form the cation right here. All right. So we should have a total of 4 structures, right? This is our 4 structures. Okay. No, we should have a total of 5 structures. No, 4. I'm sorry. So this is over here, over here. So these are all of them, whatever. Okay. So just make sure you use brackets. However you want to do it. Anyways. And so we're going to go and we're going to start from this first one here, right? Using the first one. And we're going to let's see. Right. And so from this let's see. So I'm now just realizing that I made a small mistake. It's not a mistake, but it's a mistake, and I chose the wrong position. So lesson learned. Okay, it's good for you guys. All right. My mistake, you may ask. Well, everything looks right. Everything is right, actually. But the thing that's wrong is that I chose the para position because I was not paying attention to the final product. I should have realized that. Right, so this is the original position. This is where the original position is. So this is these 2 original positions. This is ortho. I have chosen the para. I did the para substitution. Ah, okay. So I'm supposed to do ortho, and so I have done para, and that's why I was looking being a little bit perplexed here for a moment. But this is still okay. Nothing changes. It's still the same. Only difference is that this is the bond that I'm supposed to be using, not this one over here. And then from there, it's all the same stuff basically. The key will have all the right answers on it, okay? But it's the mechanism is the same. It's the exact same. And you still have 4 resonance structures. It's all the same. And so we go from we're gonna go from I'll choose the first one. It doesn't really matter too much. So I'm gonna go from the first one, and I'm going to use a Cl minus, right? Lone pair to form the aromatic structure. And then once I do, the answer has been obtained. Okay, now let's move on. Alright, synthesis. So I have to synthesize the following molecule using benzene, methanol, and any inorganic reagents. So I can only go back to methanol. So what is the first step? The first step is, well, as you may ask, first step is, let's see. Alright, So the first step I need to be careful and look at here. If you notice, actually I didn't notice first, this is not a benzene ring. So this is just, two double bonds. This is a tricky guy. So what I'm going to do is I'm going to split it right here. All right? And I made this decision, it's an ugly line, I was cut right here. So I made a decision based on two things. I want to get rid of this group that's on these benzene rings so that I can work with the benzene rings and I can work with this guy, right? And then I noticed that I have these withdrawing groups in ortho and para. So I know the reaction that I'm doing is the addition elimination. So 100 degrees Celsius. And I have this is just OCH3. Right? And then I know this is going to be a leaving group, right? Okay. And plus this is going to be O minus. Okay? So this is addition elimination. We have the strong base, we have a leaving group, right? And then we have the heat. Alright, so now let's do the right side. The right side looks a little bit trickier. So obviously this is going to be Birch reduction, the first step. So we have two double bonds. I need to go back to benzene ring. So first thing we're going to do is Na, right? So first thing is Na, CH3OH, NH3, NaNH3, and CH3OH. And this will give us back the benzene ring. You may ask, why didn't I turn this back into to a protonated alcohol first? It doesn't matter. We could do solid Na, we can do whatever. It does not change anything. This is still a donating group. This is actually a stronger donating group right here. So it doesn't matter. They're both donating groups regardless, and they're both going to be, the same way and during Birch. Okay? And so I'm going to now do this. So I can get rid of this guy by doing what? I can do addition elimination. So I need to do NaOH 2EQ because it's it's going to form an acid. NaOH 2EQ 100 degrees Celsius. And I have withdrawing group in ortho. Okay, so I go back to that. Now I have to do HNO3, H2SO4. And this is because I have a ortho para directing group and I have this meta directing deactivating group. These are both deactivating groups, but this is less deactivating, so this will direct. And so I can just add this NO2 group. And then, this one, FeBr3. Okay. And then over here, now let's do this side. So this side, we have a bromine group, NO2 group, and we have a methyl O minus group. And so what will we do? What will we do? Well, we will do Friedel-Crafts. Okay, so I want to do this. Friedel-Crafts is always the option whenever we have a carbonyl. Either I want to try to make a carbonyl so that I can do Friedel-Crafts, or I want to, if I already have a carbonyl, I can just do it right away, depending on what I have in the ring. So I need to make sure that I have at least one ring is either not deactivated or is activated. And that's going to be the ring that is the nucleophile. Other ring is going to be the Friedel-Crafts. So this cut right here, okay? And this is going to be the one that has the acid chloride. This is going to be the the nucleophile. All right, so let's do that. Okay, so this is good. And now, okay, looks good to me. Right, so this is meta, the meta. Okay, easy peasy. So SOCl2, make that. Wrong position. All right, and so to make this one, now what do I do? Okay, well, so what's the most strategic thing to do here? So the most strategic thing to do would be to remove, okay, would be to remove that NO2 group. I can remove it because I have a bromine group that is the least deactivating. So therefore it's the most directing. And therefore I can directly remove this NO2 group. And it's ortho pair directing. So this ortho pair position is blocked. So HNO3, H2SO4. Okay. So now I have this. Now what do I do? Well, if you really want to know, all I need to do now is to turn this into a, let's see. So I already have a bromine group, right? We have a couple ways to get the carboxylic acid. I can either use a Grignard and CO2 and H3O plus, but I already have a bromine group, so this I cannot use that option because then I would be going back to another bromine group on the ring, right? But I already have one. If it was something else, maybe. So I need to go a long route, which is to get a carboxylic acid in a ring, I'm gonna do side chain oxidation, so Na2, Cr. Okay, we can use that method. I'm forgetting the reagent. I know this one is easy. KMNO4, H2O, OH minus 100 degrees, and then second step, H plus. Okay, so over this. And what will this give us? This will give us a CH3 group, or any group, but let's make it a CH3 group, because that's easy for us. And now that I have a CH3 group, what can I do? Well, I can do the ortho pair reaction, and I can make this. Okay, so now I have a single CH3 group, and now to make this, I use ZN, HG, HCl, aqueous. Make sure you put that, and then this will give me, what do I want? It'll go back to an aldehyde. I don't have a choice about it. It has to go back to an aldehyde. And then to make the aldehyde, I do CO, HCl. Forgetting that this is not extending, so everyone can see. CnHG, HCl, aqueous. CO, HCl, Cu, Cl, Al, Cl3. And this will go back. Irregular benzene ring. Done. This is over here. This is done. And then all that's left is now this position right here. So I just use NaOCH3, right? And then I use 2500 psi, 350 degrees Celsius, right? And I have to do this because it's a lone OCH3 with nothing on the ring, okay? So I actually have to make the OCH3. Right, so I put 2500 psi, 350 degrees Celsius, and then I have, OCH3 minus, and I have this. So all I'm going to get is I'm going to get a benzene ring with a bromine on it. And thankfully we already synthesized this earlier, so I can just stop here. Plus OCH3 minus, which I can just do Na solid, and this gets me my methanol. Alright? And so methanol is already made over here. So everything checks out. Okay? So looks simple enough. And if you need to pause just so we can show the path more clearly. So we have this path. And then we have this path over here. Right? So everyone can see that now. And then we have, this is separated here. All right. Now moving on to spectroscopy. Okay, so we have C10, H12O2. The unsaturation number is C times 2. That's 20 plus 2, 22 minus 12. Right? This gives us 10 divided by 2 equals 5. All right? So our unsaturation number is 5. Okay? And now we have a saturation number of 5, so that very highly indicates that we have a benzene ring. All right? So we have a benzene ring. Now let's check the spec. And I know it's very hard to see here, but if you look carefully, what you have is you have these 2 peaks, right? So I now have a benzene ring which accounts for 4 out of 5 of the unsaturation number. And you have one more. I have 2 oxygens. It's very likely that one of these oxygens is a carbonyl, and they're not just all alcohol, ethers, blah blah. So I can see here that I actually have something in the 1500, 1600, 1700. So this is the 1700 region. This is an area where I have a carbonyl. So I have a carbonyl stretch right here. Okay? And so now I have that. All right, now let's check the NMR. The NMR shows to us that we have, okay, NMR shows that we have, we have in the 910 region, right, I have something. I have 1H. And so anything in the 910 region, it's always going to be a 1H peak. What this is your aldehyde. Okay? Then I have the 7-8 region, which is our benzene ring region. So here I have the doublet, 2H, 2H. And so this is going to be my benzene ring. That is para substituted. And then I have in the 4 region, I have a 2H. So I have a CH2. Box it, because this is the carbon that is, the integration number applies to. And then I have these splitting. I have 1, 2, 3 peaks minus 1. So there's a CH2 next to a CH2. But this CH2 is also, it's in the 4 region. So that means next to an oxygen. So it's connected to an O and another CH2. And then in this 2 region, I have a CH2 that looks like 1, 2, 3, 4. So this is a CH2 oxide. connected to a CH3. So 4 peaks minus 1, that's 3, is a CH3. Box it next to 1, 2, 3, minus 1. So there's a CH3 next to a CH2. These likely correlate with each other. Okay, and this one is this over here is likely, right? Okay, so this is tricky. This looks clean over here, right? But it may not be clean because I have a CH2 that's also next to a CH2. So I need to figure out, where this guy is. So it's likely also this one, but that would mean that this is a little bit more complicated than it seems. Okay? Okay, so we have that aspect. All right, so now let's start trying to piece it together. Let's start trying to piece it together. I think we have a lot of information now. All right, so I have two ends already. Right, we have ends. So I have a benzene ring, and it's para-substituted. So I have a CH3, which is the end of a molecule, right? That's the end of a chain. And then I also have an aldehyde. So aldehyde is also the end of a chain, right? It can't be in the middle. A CH3 cannot be in the middle, right? CH3 is the terminal end of any chain. So I know that I know this. So I have two oxygens. One of them is an aldehyde. And so let's try to think through some possible structures. So I have one structure just right off the bat. Right off the bat. I'm thinking this, and then I'm thinking where I have O, and then I'm thinking I have this CH2, which is next to another CH2, which is next to a CH3. And so this is what I'm proposing. All right? An alternate to this, an alternate. Let's think alternates here. And let's see, we're going to explore why other things are wrong. So obviously, if I don't have the aldehyde here, it has to be somewhere else, right? So we have one structure with aldehydes by itself. Another structure, we'll try to see if we can make it on anything else. So CH2, CH2, CH3, and then we have aldehyde. Okay, this is not correct, right? So this is connected to a carbon. This CH3 is connected to a carbon that has a hydrogen on it. That is not correct. That is not what we have here. We have a CH2 and not the splitting between a CH and a CH2 over here. So this is not correct. And if I have this like this, that means that I have, it has to be an OH here. And we have no alcohol peak, right? So the only way really that I can have both an ether and an aldehyde is if I have the ether with the R group and if I have the aldehyde by itself. And this has to look like this where all three are here is because I have the CH2, which is next to a CH2, and this CH2, which is next to a CH3. And so therefore I have to have all three groups next to each other like this. I cannot have it split up between both and have that kind of compromise. There's no way for that to occur. All right? So this is our answer. And there's only one answer. And that is the only correct possible one. Right? So, and then one other thing. So I mentioned before that if you have something between the 160 and 180 region, that gives you the identity of an ester. And this is very important to always look at, especially when you have two oxygens. But here we have a peak around, this is 160 right here. And then we have this like 165 peak. This is not what an ester will look like typically. An ester will have a deep a deep one, between the 180 and the 160 region. And if we look down, right, if we look down into our types of things on the C13 NMR, I have the carboxylic acids or esters. It's 160 to 185, right? And it's not going to be like on the edge of 160. It will be, you know, within it pretty deeply. And if you try to make an ester, you would see that, you know, it's not possible. Simply, sorry, simply because let's see what an ester looks like. Let's try another molecule, just for sake of those of you who are like, well, how do I know? Well, let's say I make an ester, right? So I have that CH2, I have that CH3. The problem is with the CH3, that's where it comes in the issue. I can't have a CH3 if I have, you know, both the aldehyde here. And we talked about already that these three groups need to be next to each other. And so I can't do that while also trying to get an ester, because an ester, you know, we have to have, and we already know that our carbonyl is within an aldehyde. So it just becomes impossible that we have an ester because we already have the aldehyde structure proven to us by the proton NMR. And the C13 NMR is not going to, like, you know, give us something contradictory to that. So this is for sure our structure. All right. So I hope this helps everyone going through this. I know it's a long video. It's an hour and 20 minutes almost. I'll try to post some timestamps throughout the video. Kind of pointless for me to say that now, but I hope this helps. I hope it's the final push to help you get the grade you want. Just make sure you really understand the concepts. They're very important in this exam. All right. I wish you all the best and good luck.